Michael Faraday stands among the most influential scientists in history, a figure whose discoveries laid the foundation for much of modern physics and electrical engineering. Though he lacked formal education, his relentless curiosity and experimental ingenuity led to groundbreaking advancements in electromagnetism and electrochemistry. Faraday's work not only transformed scientific understanding, but also had direct technological applications, making him one of the pioneers of the modern electrical age. His contributions to science, combined with his dedication to public education, ensure that his legacy remains deeply embedded in both theoretical physics and practical engineering. Born in the late 18th century, Faraday lived during a period of rapid scientific progress and industrial transformation. While many of his contemporaries were university-educated and often belonged to the elite scientific circles of Britain, Faraday emerged from humble beginnings. His journey from a bookbinder's apprentice to one of the most revered scientists of his time is a testament to his determination and intellectual brilliance. His ability to conceptualize and demonstrate physical phenomena through experiments set him apart from many of his peers. Unlike theoretical physicists who primarily worked with mathematical abstractions, Faraday relied on intuition and hands-on experimentation, making his findings more accessible and influential. Faraday's most renowned discoveries revolve around electromagnetism, a field that would later influence the development of modern electrical power systems. His discovery of electromagnetic induction, the principle behind electric transformers and generators, remains one of the most significant scientific breakthroughs of all time. Without his work, the world might have taken much longer to develop technologies such as electric motors, power grids, and wireless communication. The ability to convert mechanical energy into electrical energy, which he first demonstrated, serves as the backbone of contemporary electrical engineering. Beyond electromagnetism, Faraday also made significant contributions to chemistry. He discovered benzene, an essential compound in organic chemistry, and conducted pioneering research on the properties of gases and electrolysis. His experiments with electrolysis led to the formulation of what are now known as Faraday's laws of electrolysis, which describe the relationship between electric charge and the chemical changes it induces. These principles remain fundamental to the fields of electrochemistry and battery technology. His development of the Faraday cage, a device that blocks external electric fields, also demonstrated his deep understanding of electricity and its interactions with materials. Despite his immense contributions, Faraday remained humble throughout his career. He declined many prestigious offers, including knighthood, believing that scientific inquiry should be pursued for the advancement of knowledge rather than personal gain. His rejection of wealth and titles set him apart from many of his contemporaries and reinforced his reputation as a scientist devoted purely to discovery. His modesty and commitment to education made him not just a great scientist, but also a great teacher, inspiring countless young minds through his lectures at the Royal Institution. Faraday's impact on education was as profound as his contributions to science. His famous Christmas lectures, aimed at making science accessible to the public, continue to be a tradition at the Royal Institution in London. Through simple yet engaging demonstrations, he conveyed complex scientific principles to audiences of all ages, ensuring that scientific knowledge was not limited to an elite few. His ability to explain difficult concepts in an intuitive and visually striking manner made him one of the greatest communicators of science in history. His legacy extends beyond his discoveries and teachings. His influence shaped the work of future scientists, including James Clerk Maxwell, whose mathematical equations formalized Faraday's ideas into what we now call Maxwell's equations. These equations serve as the foundation of classical electromagnetism and paved the way for the development of radio waves, telecommunications, and modern electronics. Without Faraday's experimental work, Maxwell's theories might never have been developed, showing how fundamental his contributions were to the advancement of physics. Faraday's work also laid the groundwork for the Second Industrial Revolution, which saw the widespread use of electricity in industry and daily life. His discoveries enabled the design of electrical generators and motors, making large-scale electricity production and distribution possible. Today, almost every electrical device, from household appliances to power plants, operates on principles that Faraday uncovered nearly 2 centuries ago. The modern world, with its dependence on electricity, is a direct outcome of the foundations he established. Even in the 21st century, Faraday's influence remains undeniable. His discoveries continue to drive technological innovation, from electric vehicles to renewable energy systems. The principles of electromagnetism that he pioneered are fundamental to modern physics, engineering, and material science. His work exemplifies the power of curiosity-driven research, showing that even without formal education, a dedicated mind can change the world. His story is a powerful reminder that scientific progress is not confined to those with privilege, but is accessible to anyone with passion and perseverance. The story of Michael Faraday is one of perseverance, curiosity, and an unwavering commitment to knowledge. Unlike many of his scientific contemporaries, Faraday did not come from a privileged background nor receive a formal education in the sciences. Instead, he was born into a working-class family and faced numerous social and economic barriers that could have easily prevented him from pursuing a career in science. However, his determination to learn and his self-taught approach to education allowed him to break through these obstacles. His early life played a crucial role in shaping the scientist he would later become, instilling in him the values of humility, hard work, and relentless curiosity. Michael Faraday was born on September 22, 1791, in Newington Butts, a small village that is now part of South London. His family was poor, and his father, James Faraday, was a blacksmith who struggled to provide for his wife and 4 children. The Faradays belonged to the Sandemanian religious sect, a strict and devout Christian group that emphasized humility, discipline, and community service. While their religious beliefs encouraged intellectual modesty, they also fostered a sense of duty and diligence that would remain central to Faraday's character throughout his life. Because of his family's financial struggles, Faraday received only a basic education. He attended a local school where he learned to read, write, and perform simple arithmetic, but his formal schooling ended at the age of 13. Unlike many great scientists of his time, who studied at prestigious universities like Cambridge or Oxford, Faraday's academic foundation was limited. However, what he lacked in formal education, he made up for with an insatiable desire to learn. He was naturally inquisitive and sought knowledge in unconventional ways. At the age of 14, Faraday became an apprentice to George Ribot, a bookbinder and bookseller in London. This apprenticeship was a turning point in his life. Working in a bookshop surrounded him with a vast collection of books, which he eagerly devoured in his free time. He was particularly drawn to books on science, especially chemistry and electricity. One book that had a profound impact on him was the Encyclopedia Britannica, from which he learned about electricity, a subject that fascinated him deeply. Another influential text was Conversations on Chemistry by Jane Marcet, which presented scientific concepts in a clear and accessible manner. Faraday's exposure to scientific literature not only expanded his understanding, but also ignited a passion for experimentation. In the back room of the bookshop, he began conducting small experiments using rudimentary materials. He built simple electrostatic devices and attempted to recreate the experiments he read about in books. This hands-on approach to learning became a defining characteristic of his scientific career. Unlike many theorists of his time, Faraday always preferred experimental investigation over abstract mathematical reasoning. His growing interest in science soon led him beyond books and into the world of public lectures. In 1812, a pivotal opportunity arose when a customer at the bookshop, noticing Faraday's enthusiasm for science, gave him tickets to attend a series of lectures by Sir Humphry Davy at the Royal Institution. Davy was one of the most famous scientists of the time, known for his discoveries in chemistry and his work with gases. Faraday eagerly attended these lectures, taking meticulous notes and binding them into a book for his personal study. The clarity and excitement with which Davy presented his experiments inspired Faraday, reinforcing his dream of becoming a scientist. Faraday's determination to enter the scientific community led him to take an extraordinary step. He wrote a letter to Humphrey Davy, expressing his admiration and including his lecture notes as proof of his dedication. Davy was impressed by Faraday's enthusiasm and the precision of his notes, but initially had no position to offer him. However, fate intervened when an assistant at the Royal Institution was dismissed and Davy recommended Faraday for the position. In 1813, at the age of 21, Faraday was hired as a laboratory assistant at the Royal Institution, marking the beginning of his formal scientific career. His new role was far from glamorous. Initially, he was responsible for cleaning equipment, preparing chemical samples, and assisting in experiments conducted by senior scientists. However, Faraday saw these tasks as invaluable learning opportunities. He worked diligently, observing every experiment, asking questions, and refining his own techniques. His hands-on experience in the laboratory was equivalent to an informal scientific education, and it allowed him to develop a deep understanding of experimental methods. Faraday's early years of the Royal Institution were also marked by a unique opportunity. He accompanied Humphrey Davy on a European scientific tour. Between 1813 and 1815, he traveled across Europe, meeting some of the most distinguished scientists of the era, including André-Marie Ampère and Alessandro Volta. This experience exposed him to cutting-edge research and gave him insights into the broader scientific community. Though he was still regarded as an assistant rather than a peer, the knowledge he gained during this journey would later prove invaluable in his own experiments. Despite his achievements, Faraday never let go of the humility that defined his character. Even as he gained recognition, he remained deeply connected to his working-class roots and his Sandemanian faith. Unlike many of his contemporaries, who sought personal fame and fortune, Faraday pursued science as a means to understand the natural world and benefit humanity. His early struggles and self-taught background gave him a unique perspective on learning, making him not only a brilliant scientist, but also an inspiring teacher who believed in making science accessible to all. Faraday's journey from a poor, uneducated boy to a respected scientist is a testament to the power of perseverance and self-education. His early life experiences instilled in him a love for experimentation, a relentless curiosity, and a commitment to knowledge that would define his career. While many scientists rely on academic training, Faraday proved that passion and determination can be just as powerful in shaping a great mind. His rise from a bookbinder's apprentice to one of the greatest experimental scientists in history is a story of inspiration, demonstrating that knowledge is not confined to privilege, but is accessible to those who seek it with dedication. Michael Faraday's journey into the scientific world was not one of privilege or ease, but of relentless perseverance. His apprenticeship as a bookbinder had introduced him to the world of knowledge, but it was his determination that ultimately led him to the doorstep of the Royal Institution. This transition from an inquisitive bookbinder to a respected scientist was not instantaneous. Rather, it was the result of a series of fortunate events, careful decisions, and an insatiable desire to learn. His entry into science marked a turning point in his life and set the stage for the discoveries that would later revolutionize physics and chemistry. Faraday's first major opportunity came in 1812 when he attended a series of lectures by Sir Humphrey Davy, one of the most prominent chemists of the time. Davy's work in electrochemistry and his discoveries of elements, such as potassium and sodium, had already cemented his reputation as a leading scientist. For Faraday, witnessing Davy's experiments firsthand was nothing short of transformative. These lectures introduced him not only to advanced scientific concepts, but also to the idea that experimentation was the key to discovery. More importantly, Davy's ability to communicate complex ideas in an engaging and accessible manner left a lasting impression on the young Faraday. Determined to transition from an observer to an active participant in science, Faraday took an extraordinary step. He wrote to Humphrey Davy, expressing his admiration and enclosing meticulous notes he had taken during the lectures. In his letter, he politely requested an opportunity to work in Davy's laboratory. This act of initiative was remarkable for someone of Faraday's background, especially in an era where class distinctions were rigid. His request demonstrated not only his eagerness, but also his ability to organize and present scientific information clearly, an ability that would define his career. Davy, though initially unable to offer him a position, was impressed by Faraday's dedication. He recognized the young man's potential, but, at the time, had no vacancies for an assistant. However, fate soon intervened. In 1813, an assistant at the Royal Institution was dismissed for misconduct, creating an opening. Remembering Faraday's letter and his enthusiasm, Davy recommended him for the position. Just like that, Faraday was given a rare opportunity to enter the world of experimental science, an opportunity that would shape the rest of his life. Faraday's early days at the Royal Institution were far from glamorous. His duties included cleaning glassware, preparing chemical samples, and assisting with demonstrations. He was not treated as an equal among scientists, but rather as a mere laboratory assistant. However, instead of viewing these tasks as menial labor, Faraday embraced them as an opportunity to learn. He carefully observed every experiment conducted by Davy and other scientists, absorbing knowledge like a sponge. His practical skills improved rapidly, and his keen attention to detail made him an invaluable member of the laboratory. His most significant early experience came in 1813 when Davy embarked on a grand tour of Europe, visiting leading scientific institutions and meeting distinguished scholars. Faraday was invited to join the expedition as Davy's assistant, a role that was both an incredible opportunity and a personal challenge. Though he was thrilled at the chance to meet scientific luminaries such as Alessandro Volta and André-Marie Ampère, Faraday was often treated more as a servant than as an aspiring scientist. Davy's wife, in particular, regarded him as a lowly attendant rather than a colleague. Despite this, Faraday remained focused on the intellectual aspects of the journey, carefully observing experiments and engaging with scientific discussions whenever possible. This European tour was crucial to Faraday's development. He witnessed firsthand the latest advancements in chemistry and physics, gaining insights that he would later incorporate into his own research. Exposure to leading scientific minds expanded his perspective and reinforced his belief that experimentation was the most powerful tool for understanding nature. Although he returned to England still regarded as an assistant, he had acquired knowledge that far exceeded his formal role. Upon returning to the Royal Institution, Faraday resumed his work, but now with a renewed sense of purpose. He continued assisting Davy in experiments, particularly in the field of electrochemistry. Under Davy's mentorship, he honed his understanding of chemical reactions and electrical phenomena. Over time, he began conducting his own experiments, demonstrating both creativity and precision. His ability to design and execute experiments independently was becoming increasingly apparent. Despite his growing expertise, Faraday faced significant barriers to recognition. The scientific community of early 19th century Britain was dominated by men of wealth and formal education, making it difficult for someone of Faraday's background to gain credibility. However, his work ethic and contributions could not be ignored. Slowly but surely, he started to publish scientific papers and gain respect among his peers. By the mid-1820s, he had established himself as more than just Davy's assistant. He was emerging as a scientist in his own right. Faraday's apprenticeship and entry into science were defining periods of his life. His willingness to work tirelessly, his ability to learn from observation, and his determination to seize every opportunity set him apart. Though he began as a laboratory assistant performing routine tasks, his insatiable curiosity and rigorous approach to experimentation allowed him to rise beyond his humble beginnings. This transition from a bookbinder's apprentice to a scientific researcher was not just a personal triumph. It was a testament to the power of perseverance, proving that talent and hard work could overcome social and educational barriers. Before Michael Faraday revolutionized electromagnetism, he made significant contributions to chemistry. His early research in this field demonstrated not only his ingenuity as an experimentalist, but also his ability to bridge scientific disciplines. From discovering new chemical compounds to refining electrochemical techniques, Faraday's work in chemistry laid the foundation for his later discoveries in physics. His meticulous approach to experimentation, combined with an intuitive understanding of natural processes, enabled him to make groundbreaking contributions that would influence generations of scientists. Faraday's initial foray into chemistry was largely influenced by his mentor, Sir Humphry Davy, one of the leading chemists of the early 19th century. Under Davy's guidance at the Royal Institution, Faraday worked extensively with gases, metals, and electrochemical reactions. His ability to conduct precise and controlled experiments quickly gained him recognition, and he soon moved beyond assisting Davy to conducting independent research. His work with chlorine and other reactive elements led to some of his earliest significant discoveries, showcasing his talent for experimentation. One of Faraday's most notable chemical discoveries was benzene, a fundamental hydrocarbon that would become essential in organic chemistry. In 1825, while studying illuminating gas produced from whale oil, he isolated a new compound with distinct properties. He named it benzene, unaware at the time of its future significance. Today, benzene serves as a building block for numerous industrial and pharmaceutical products, and its discovery remains one of Faraday's lasting contributions to chemistry. Faraday also played a key role in advancing electrochemistry, a field pioneered by scientists such as Alessandro Volta and Humphry Davy. His experiments with electrolysis, the process of using electricity to drive chemical reactions, led him to develop what are now known as Faraday's laws of electrolysis. These laws quantitatively describe the relationship between electric charge and the amount of substance deposited or dissolved during an electrochemical reaction. His findings provided a mathematical framework that connected chemistry with electrical science, forming the basis for later advancements in battery technology and electroplating. His work on electrolysis also led to the introduction of key scientific terminology. Faraday coined terms such as anode, cathode, electrode, and ion, which are still in use today. These terms helped standardize the language of electrochemistry, making it easier for scientists to communicate their findings. By establishing a systematic approach to electrochemical reactions, Faraday significantly advanced the study of electricity and its interactions with matter. Beyond electrochemistry, Faraday's work extended into metallurgy and material science. He conducted experiments on the properties of various metals, studying their behavior under different conditions. His investigations into steel alloys contributed to improvements in the production of stronger and more durable materials, which had practical applications in industry and engineering. Although he is more often associated with electromagnetism, Faraday's influence on material science highlights the breadth of his scientific interests. Another remarkable contribution of Faraday to chemistry was his development of the Faraday cage, a structure that blocks external electric fields. Although this invention is often associated with his later work in electricity, its implications for chemical research were immediate. The ability to shield sensitive experiments from electrical interference allowed for more precise chemical measurements, further demonstrating Faraday's innovative approach to problem solving. Faraday's chemical research was not limited to academic curiosity. It had practical implications that benefited industry and society. His work with gases, for example, contributed to the development of improved lighting systems. At a time when cities were transitioning from candlelight to gas lighting, Faraday's insights helped refine the production of illuminating gases, making public lighting more efficient and widespread. Similarly, his research on corrosion and metal coatings provided valuable information for engineers working on infrastructure and manufacturing. Despite his significant achievements in chemistry, Faraday remained deeply committed to experimental integrity. He was meticulous in recording his observations and was known for repeating experiments multiple times to verify his results. Unlike some scientists who were driven by personal ambition or financial gain, Faraday was primarily motivated by a desire to understand nature and share knowledge. His humility and dedication to scientific inquiry earned him respect among his peers, even as he continued to challenge established ideas. Faraday's contributions to chemistry were instrumental in shaping his later work in physics. His understanding of atomic interactions, gained through his studies of electrochemistry, provided the conceptual foundation for his investigations into electromagnetism. Though he eventually became more famous for his work in electricity and magnetism, his chemical research remained an essential part of his scientific legacy. Without his early experiments in electrochemistry and material science, his later breakthroughs in electromagnetism might not have been possible. Michael Faraday's most defining scientific achievement was the discovery of electromagnetic induction, a breakthrough that would lay the foundation for modern electrical technology. This discovery was not the result of chance, but rather the culmination of years of rigorous experimentation, deep curiosity, and an unwavering belief in the relationship between electricity and magnetism. At a time when scientists were still grappling with the nature of these forces, Faraday's work provided the missing link, demonstrating that electricity could be generated from magnetism. This revelation changed the course of science and technology, paving the way for the development of electric generators, transformers, and, ultimately, the electrical power systems that define modern civilization. By the early 19th century, electricity and magnetism were understood as separate forces, but there were hints that they might be connected. In 1820, Danish physicist Hans Christian Ørsted discovered that an electric current could produce a magnetic field, an observation that suggested a relationship between the two phenomena. This discovery sparked intense interest among scientists, including André-Marie Ampère and François Arago, who sought to further explore the connection between electricity and magnetism. However, while Ørsted had demonstrated that electricity could influence magnetism, no one had yet shown that the reverse was possible, whether magnetism could generate electricity. Faraday, always guided by experimental observation, became determined to find this missing link. He hypothesized that if a magnetic field could be made to change in some way, it might induce an electric current in a nearby conductor. He embarked on a series of systematic experiments, testing various configurations of magnets and coils of wire in an attempt to generate electricity. His persistence and ingenuity in designing experiments would prove to be the key to one of the most significant discoveries in physics. In 1831, after years of investigation, Faraday finally succeeded in demonstrating electromagnetic induction. In his now famous experiment, he wrapped two separate coils of wire around an iron ring. One coil was connected to a battery, creating a steady electric current and, consequently, a magnetic field in the iron ring. The other coil was connected to a galvanometer, an instrument used to detect electric currents. To his excitement, Faraday observed that when he turned the battery on or off, a brief current appeared in the second coil, even though there was no direct electrical connection between the two. This indicated that the changing magnetic field in the iron ring was inducing an electric current in the second coil. Faraday's discovery demonstrated that an electric current could be produced by a changing magnetic field, a phenomenon that would later be described by Faraday's law of induction. This law states that the induced voltage in a circuit is proportional to the rate of change of the magnetic flux through the circuit. In other words, electricity could be generated by moving a magnet through a coil of wire or by changing the intensity of a magnetic field around a conductor. This principle became the foundation for electric power generation, forming the basis of technologies such as transformers, inductors, and electric generators. Faraday's breakthrough had profound implications. Until then, electricity had been generated primarily through chemical reactions, such as in batteries, which provided only limited and short-lived power. Faraday's work showed that mechanical energy, such as the motion of a magnet, could be converted into electrical energy, opening the door for large-scale power generation. This laid the groundwork for the development of electrical generators, which would later drive the Industrial Revolution and modern electrical grids. The significance of Faraday's discovery extended beyond practical applications. His work provided crucial experimental evidence for the broader theory of electromagnetism, which was later mathematically formulated by James Clerk Maxwell. Maxwell's equations, which describe the behavior of electric and magnetic fields, were directly inspired by Faraday's experiments. In this way, Faraday's work not only led to technological advancements, but also contributed to one of the most important theoretical frameworks in physics. Despite the groundbreaking nature of his discovery, Faraday remained humble. He viewed science as a pursuit of knowledge rather than a means of personal gain. Unlike many of his contemporaries who sought patents for their inventions, Faraday never attempted to profit from his work. Instead, he dedicated himself to further research and to sharing his findings with the scientific community. His lectures at the Royal Institution, where he demonstrated the principles of electromagnetic induction with simple and elegant experiments, inspired generations of scientists and engineers. Faraday's work on induction also led to other important discoveries, including the concept of self-induction, where a changing current in a coil can induce a voltage within the same coil. This principle is fundamental to modern electrical circuits and devices, including transformers and inductors used in power systems and radio technology. His ability to translate abstract scientific ideas into practical applications made his contributions invaluable to both theoretical physics and engineering. The discovery of electromagnetic induction was a turning point not only in Faraday's career, but also in the history of science. His ability to recognize patterns in nature, design meticulous experiments, and draw profound conclusions from simple observations set him apart as one of the greatest experimental scientists of all time. His findings reshaped humanity's understanding of electricity and magnetism, bridging the gap between fundamental research and real-world technological advancements. More than a century later, every generator, motor, and transformer in operation continues to rely on the principles Faraday uncovered. Following his groundbreaking discovery of electromagnetic induction, Michael Faraday continued to push the boundaries of scientific understanding, particularly in the study of electric and magnetic fields. His innovative approach to experimentation and his ability to conceptualize forces in space led to the development of the concept of the electromagnetic field, an idea that would later become central to modern physics. Though he lacked formal mathematical training, Faraday's insights laid the foundation for James Clerk Maxwell's electromagnetic theory, which ultimately shaped our understanding of electromagnetism and light. One of Faraday's greatest strengths was his ability to visualize physical phenomena in ways that other scientists could not. At a time when electricity and magnetism were largely understood as forces acting at a distance, Faraday introduced the idea that these forces existed within fields, invisible regions of influence surrounding electric charges and magnets. He proposed that electrical and magnetic forces did not act instantaneously over a distance, but rather were transmitted through a medium, creating continuous interactions in space. This idea was revolutionary and marked a shift away from the traditional Newtonian view of action at a distance. Faraday's concept of fields emerged from his careful observations of magnetic lines of force. In a series of experiments, he placed iron filings near magnets and noticed that they aligned along curved paths. These patterns, which revealed the structure of magnetic fields, suggested that magnetism was not confined to discrete points, but instead filled the surrounding space. Faraday extended this reasoning to electricity, proposing that electric charges also produced fields that influenced other charges around them. His experiments demonstrated that these fields could be manipulated, leading to the development of practical applications such as transformers and inductors. One of his key insights was that changing magnetic fields could induce electric currents, a principle he had already demonstrated in electromagnetic induction. However, he took this idea further by suggesting that a changing electric field might, in turn, produce a magnetic field. Although he could not mathematically formulate this idea, it was a crucial step toward understanding the true nature of electromagnetism. Faraday's ideas would later inspire Maxwell, who translated them into a set of equations that fully described the behavior of electric and magnetic fields. Faraday also explored the interaction between electricity and matter. His experiments on dielectric materials or insulators, provided early evidence that electric fields could penetrate and polarize substances, leading to the concept of electrical capacitance. This work was instrumental in understanding how electrical energy is stored and transmitted, laying the groundwork for future advancements in electronics and telecommunications. His investigations into the properties of materials and electric fields anticipated later discoveries in solid-state physics and quantum mechanics. Another major breakthrough came with Faraday's work on Faraday rotation, a phenomenon in which the polarization of light is rotated when it passes through a material in the presence of a magnetic field. This was one of the first pieces of evidence that electricity, magnetism, and light were interconnected. His discovery suggested that light itself might be an electromagnetic wave, a hypothesis that Maxwell later confirmed through his mathematical formulation of electromagnetism. This realization ultimately led to the development of radio waves, X-rays, and modern communication technologies. Faraday's field theory had profound implications for science and engineering. Before his work, most electrical applications relied on direct electrical conduction through wires. However, his discovery showed that electrical energy could be transmitted through space, leading to the development of wireless communication technologies. Later scientists, including Nikola Tesla and Heinrich Hertz, built upon Faraday's principles to create the foundations of radio and wireless electricity. Despite his immense contributions, Faraday's ideas were initially met with skepticism. Many scientists of his time were uncomfortable with the concept of invisible fields and preferred mathematical models based on direct forces between charged particles. However, as experimental evidence accumulated, his field theory gained acceptance and became a fundamental part of physics. Today, the concept of fields is central to our understanding of not only electromagnetism, but also gravity, quantum mechanics, and even modern theories of spacetime. Faraday's work on fields also influenced the development of electromechanical devices. His experiments with coils, transformers, and inductors directly contributed to the design of early electrical generators and motors. By demonstrating how changing fields could induce currents, he paved the way for the practical generation and transmission of electrical power, which would later drive industrial and technological progress worldwide. His discoveries continue to underpin modern electrical engineering, from power grids to microelectronics. Michael Faraday's discoveries in electromagnetism and electrochemistry were not confined to theoretical advancements. They had profound practical implications that shaped the development of modern electrical technology. His pioneering work on electromagnetic induction, electrolysis, and the concept of electromagnetic fields directly influenced the creation of electric generators, transformers, and motors. These technological innovations laid the foundation for the electrical power systems that drive industries, transportation, and daily life today. Faraday's research not only expanded scientific knowledge, but also provided the tools for engineers and inventors to harness electricity for practical applications. One of the most direct outcomes of Faraday's work was the invention of the electric generator. His discovery of electromagnetic induction demonstrated that a changing magnetic field could generate an electric current in a conductor. This principle led to the design of the first dynamo, an early form of an electric generator. Though Faraday's own models were rudimentary, his experiments inspired later inventors, such as Werner von Siemens and Thomas Edison, to develop more efficient and powerful generators. Today, nearly all electricity is produced using Faraday's principles, whether in hydroelectric dams, wind turbines, or nuclear power plants. Faraday's insights also played a crucial role in the development of electric motors. Just as he had demonstrated that a moving magnet could induce electricity in a wire, he also showed that an electric current passing through a wire could produce motion when placed within a magnetic field. This principle became the foundation of electric motors, which convert electrical energy into mechanical energy. From industrial machinery to household appliances, electric motors are now indispensable in modern technology. Faraday's work directly influenced later inventors, such as Nikola Tesla, who refined and expanded on his ideas to create alternating current, AC motors. Another major technological advancement, based on Faraday's discoveries, was the transformer, a device that allows electrical energy to be transmitted efficiently over long distances. Faraday's experiments demonstrated that alternating magnetic fields could induce currents in nearby conductors, a principle that engineers later used to develop transformers. These devices enabled the efficient transmission of electricity from power plants to homes and industries, making large-scale electrification possible. Without Faraday's foundational discoveries, the modern electrical grid would not exist. Beyond power generation and transmission, Faraday's contributions extended into the realm of telecommunication. His experiments with electromagnetic fields and conductors provided the scientific foundation for technologies such as the telegraph and the telephone. Although Faraday did not directly invent these devices, his discoveries allowed inventors like Samuel Morse and Alexander Graham Bell to develop practical communication systems. The understanding of electromagnetic waves, which later enabled radio, television, and wireless communication, also stemmed from Faraday's pioneering research. Faraday's influence was not limited to large-scale power and communication systems. His work also impacted battery technology. His studies of electrolysis and electrochemical reactions contributed to the development of better batteries, which were essential for portable power sources. Later scientists, including John Daniel and Gaston Planté, built upon Faraday's electrochemical research to create more efficient and longer-lasting batteries, which are now essential in everything from mobile phones to electric vehicles. In addition to inspiring technological advancements, Faraday played a key role in the standardization of electrical units and terminology. He introduced terms such as electrode, cathode, anode, and ion, which remain fundamental in chemistry and physics today. His systematic approach to measuring electrical phenomena also contributed to the eventual development of standardized units of electricity, such as the farad, a unit of electrical capacitance named in his honor. This standardization allowed scientists and engineers to communicate more effectively and advance electrical science in a structured way. Faraday's impact extended beyond technical contributions. His work also influenced the philosophy of scientific inquiry. His emphasis on experimentation, careful observation, and the rejection of speculation without empirical evidence set a high standard for scientific research. He demonstrated that even without advanced mathematical training, rigorous experimentation could lead to profound discoveries. His experimental methods continue to serve as a model for modern scientists and engineers seeking to understand and manipulate physical phenomena. Despite the immense technological implications of his work, Faraday remained a humble and selfless scientist, refusing to patent his discoveries. Unlike many of his contemporaries who sought financial gain from their inventions, Faraday believed that knowledge should be freely shared for the benefit of society. His decision not to profit from his discoveries allowed his research to be widely adopted and further developed by others, accelerating the progress of electrical technology. His commitment to public education, including his famous Christmas lectures at the Royal Institution, also helped disseminate scientific knowledge to wider audiences. Michael Faraday's influence extended far beyond his groundbreaking discoveries in electromagnetism and electrochemistry. His contributions to scientific thought and education played a crucial role in shaping how science was conducted, taught, and understood. A visionary not only in research, but also in communication, Faraday devoted much of his life to making scientific knowledge accessible to all. His unique ability to bridge the gap between complex scientific concepts and public understanding left a lasting impact on generations of scientists, students, and educators. One of Faraday's most significant contributions to scientific thought was his emphasis on empirical observation and experimentation. At a time when theoretical speculation often outpaced experimental evidence, Faraday remained steadfast in his belief that science should be based on careful observation and reproducible experiments. His work demonstrated that even without advanced mathematical training, a scientist could make profound discoveries through meticulous experimentation. This approach reinforced the modern scientific method, ensuring that hypotheses were tested against real-world results rather than merely inferred from existing theories. Faraday's commitment to experimentation was evident in his notebook recordings, where he meticulously documented his findings. His detailed notes not only provided clarity for his own research, but also served as a valuable resource for future scientists. This practice of rigorous documentation became a model for laboratory work, influencing how modern researchers structure their experiments and record data. His emphasis on accuracy and transparency helped establish the foundation for modern scientific research protocols. Beyond his own research, Faraday was passionate about scientific education and public engagement. Unlike many scientists of his time, who communicated primarily with their academic peers, Faraday believed that science should be accessible to everyone, regardless of background or social status. He was a firm believer that knowledge was a public good, and he worked tirelessly to make science understandable and exciting for the general public. His ability to explain complex concepts in simple terms made him one of the most effective science communicators of his era. One of his greatest contributions to education was the establishment of the Royal Institution Christmas Lectures, a series of public science lectures aimed at young audiences. First delivered in 1825, these lectures became an annual tradition and continue to this day. Faraday's presentations were renowned for their clarity, enthusiasm, and engaging demonstrations, which made science both comprehensible and thrilling. His ability to captivate audiences, young and old, helped foster a widespread appreciation for scientific inquiry and discovery. Faraday's lectures covered a wide range of topics, from the properties of electricity and magnetism to the nature of gases and chemical reactions. What set his lectures apart was his use of live demonstrations, where he performed experiments in front of audiences to illustrate scientific principles in action. These visual and interactive elements made abstract scientific concepts tangible and engaging, a teaching method that remains widely used in science education today. In addition to his public lectures, Faraday made significant efforts to promote science education in schools. He advocated for the inclusion of experimental science in school curriculums, arguing that hands-on learning was essential for developing critical thinking skills. His influence helped shift education from rote memorization of facts toward an emphasis on inquiry-based learning. This approach encouraged students to question, observe, and test ideas, fundamental skills for scientific advancement. Faraday's impact on education was not limited to children and students. He also sought to educate policymakers and industrialists about the importance of scientific research. He believed that scientific knowledge should inform public policy and industrial development, and he frequently advised the British government on matters related to chemistry, electricity, and engineering. His ability to communicate scientific concepts to non-specialists ensured that his insights had practical applications in fields ranging from public health to national defense. Despite his lack of formal education, Faraday's influence on the academic world was immense. His experimental discoveries formed the foundation for electromagnetic theory, which was later mathematically formalized by James Clerk Maxwell. Maxwell himself acknowledged Faraday's profound influence, stating that Faraday's visual and conceptual approach to electromagnetism was the inspiration for his own theoretical work. Faraday's contributions thus bridged the gap between experimental physics and mathematical physics, shaping the trajectory of modern science. Michael Faraday was not only a pioneering scientist, but also a man of profound integrity and humility. His approach to scientific inquiry was deeply rooted in ethical principles, a rare quality in an era when personal ambition and financial gain often influenced scientific endeavors. Faraday's unwavering commitment to knowledge for the sake of human progress, rather than personal enrichment, set him apart from many of his contemporaries. His ethical stance, combined with his scientific brilliance, cemented his legacy as one of the most respected figures in the history of science. One of the most remarkable aspects of Faraday's character was his refusal to patent his discoveries. At a time when many inventors sought to profit from their innovations, Faraday chose to make his work freely available to the scientific community and society at large. He believed that knowledge should be shared for the benefit of humanity rather than monopolized for personal gain. This decision allowed his discoveries in electromagnetism and electrochemistry to be widely adopted and developed further, accelerating technological advancements that continue to shape the modern world. Faraday's ethical approach was also evident in his commitment to honesty and transparency in scientific research. He rejected speculation that was not grounded in empirical evidence and was known for his meticulous documentation of experiments. He believed that scientific knowledge should be built upon verifiable facts, not assumptions or untested theories. His rigorous methodology set a standard for scientific integrity that continues to guide researchers today. His notebooks, filled with precise experimental observations, serve as a testament to his dedication to accuracy and truth. Another key aspect of Faraday's ethical philosophy was his commitment to public service. He did not see science as an isolated pursuit, but as a discipline that should directly benefit society. Throughout his career, he provided scientific advice to the British government on various issues, including the improvement of lighthouse illumination, the prevention of industrial explosions, and the safe handling of chemical substances. His contributions to public safety and engineering had practical applications that extended beyond the laboratory, impacting everyday life in meaningful ways. Faraday's humility and dedication to education further demonstrated his ethical values. Despite his vast knowledge and contributions, he remained deeply humble and accessible, never seeking personal recognition or titles. He declined offers of knighthood, stating that he preferred to be remembered as plain Michael Faraday. Similarly, he refused to serve as the president of the Royal Society, believing that his true calling was research and teaching rather than administration. This humility endeared him to both colleagues and students, reinforcing his reputation as a scientist motivated by curiosity rather than prestige. His religious beliefs also played a role in shaping his ethical outlook. As a devout member of the Sandemanian Christian sect, Faraday adhered to principles of humility, service, and honesty. Though he never attempted to use religion to justify his scientific work, his faith reinforced his dedication to ethical conduct and his belief that scientific knowledge should be pursued for the good of all. This ethical grounding helped him navigate scientific debates with patience and respect, even when his ideas were met with skepticism. Faraday's influence extended beyond his lifetime, shaping the way future scientists approached both research and ethics. His work inspired James Clerk Maxwell, who mathematically formalized Faraday's ideas on electromagnetism, leading to the development of modern physics. Albert Einstein later regarded Faraday as one of his greatest inspirations, stating that Faraday's field concept laid the groundwork for relativity. The far-reaching consequences of Faraday's discoveries illustrate how his scientific and ethical principles continue to resonate in the modern world. One of the most enduring aspects of Faraday's legacy is the scientific institutions and educational programs that bear his name. The Faraday Institute for Science and Religion explores the relationship between scientific inquiry and ethical considerations. The Faraday Medal, awarded by the Institution of Engineering and Technology, recognizes outstanding contributions to electrical science and engineering. These honors reflect the lasting impact of Faraday's work and values, ensuring that his influence continues to guide scientific progress. Today, as society faces ethical dilemmas related to technological advancements, such as artificial intelligence, genetic engineering, and environmental sustainability, Faraday's principled approach to science remains more relevant than ever. His belief that knowledge should be used for the greater good, rather than personal or corporate gain, serves as a guiding philosophy for responsible scientific innovation. His emphasis on transparency, integrity, and education continues to inspire researchers, educators, and policymakers alike. Michael Faraday's impact on modern science and technology cannot be overstated. His discoveries in electromagnetism, electrochemistry, and physics fundamentally shaped the course of scientific progress and technological development. Faraday's principles remain the foundation for numerous fields, from electrical engineering to quantum mechanics, and his contributions continue to influence both theoretical and applied sciences. His life and work exemplify how scientific exploration can transform society, inspire innovation, and leave an indelible mark on the world. One of Faraday's most enduring legacies is his fundamental contributions to electromagnetism. His work laid the groundwork for Maxwell's equations, which mathematically unified electricity, magnetism, and light. Maxwell's formulation of these equations provided the theoretical basis for much of modern physics, including theories of electromagnetism, relativity, and quantum mechanics. Faraday's conceptualization of electromagnetic fields, though not fully developed in mathematical terms, was integral to Maxwell's success. His field theory changed the way we view the forces of nature, as it emphasized that electric and magnetic fields are not isolated phenomena, but interconnected and dynamic entities that permeate space. Faraday's influence extended beyond electromagnetism into the realm of modern technology, where his discoveries continue to shape everyday life. His work on electromagnetic induction directly led to the invention of the electric generator, which is still the primary method of generating electricity worldwide. The electric motor, based on Faraday's experiments with current and magnetic fields, powers countless devices from industrial machinery to household appliances. Today, the vast global network of electricity generation, transmission, and consumption would be unimaginable without Faraday's pioneering research. The transformer, another key invention stemming from Faraday's work, made the efficient transmission of electrical power over long distances possible. His discovery that varying magnetic fields could induce currents in nearby conductors led to the creation of transformers, which now form the backbone of modern power grids. Faraday's contributions to power distribution technologies helped usher in the era of electrification that powered industrialization and facilitated the technological advances of the 20th and 21st centuries. His work continues to influence electrical engineers and physicists striving to meet the ever-growing demand for efficient and sustainable energy systems. Faraday's exploration of electricity and chemistry also had profound implications for the development of the modern chemical industry. His discovery of the principles of electrolysis and the identification of the relationship between electric currents and chemical reactions paved the way for innovations in electroplating, battery technology, and the production of various chemicals. The concept of electrochemical cells, which Faraday elucidated, remains foundational to the design of modern batteries and fuel cells. His work has played a significant role in the development of renewable energy technologies, such as solar power and hydrogen fuel cells, which rely on electrochemical processes. Moreover, Faraday's contributions to the understanding of light and optics continue to resonate in modern physics. His discovery of the Faraday effect, in which the polarization of light rotates when passed through a magnetic field, provided early evidence that light was an electromagnetic wave. This was a precursor to the wave theory of light and eventually led to the development of the theory of electromagnetic radiation. Faraday's insights, along with the work of later scientists like James Clerk Maxwell, Albert Einstein, and Max Planck, contributed to the birth of quantum mechanics and the study of light as both a particle and a wave. Faraday's approach to scientific inquiry and education also continues to influence contemporary scientific culture. His emphasis on hands-on experimentation and his commitment to making science accessible to the public established a model for science education that prioritizes active learning and engagement. Faraday's Royal Institution Christmas lectures, in particular, helped establish science as something not reserved for scholars, but as a field of knowledge that could excite and inspire people of all ages. His legacy in science communication endures through the continuing tradition of public lectures, scientific demonstrations, and outreach programs that aim to make science both understandable and engaging for everyone. In addition to his scientific and educational contributions, Faraday's ethical approach to science remains an important part of his legacy. His refusal to patent his discoveries and his belief in the free dissemination of knowledge set a standard for scientific integrity. Faraday's example of prioritizing public service over personal gain continues to inspire contemporary scientists who navigate the complexities of modern research and commercialization. In an age where the ethics of scientific research are frequently debated, Faraday's commitment to truth, humility, and the betterment of humanity stands as a timeless model for responsible scientific practice. Faraday's influence also extends to modern physics. His work on electromagnetic fields, though not fully understood in his time, provided the conceptual framework that would later be formalized by James Clerk Maxwell and developed further by 20th century physicists such as Albert Einstein and Richard Feynman. The idea of fields, which Faraday visualized as a continuous, dynamic entity, has become central to our understanding of not only electromagnetism, but also gravitational fields and the structure of space-time. Faraday's intuitive grasp of these abstract concepts has had a lasting impact on theoretical physics and continues to shape the way physicists think about the universe. The impact of Faraday's work also extends to modern technology, particularly in the fields of computing and telecommunications. The principles of electromagnetic induction and electric circuits, first discovered by Faraday, underpin the operation of computers, mobile phones, and the internet. The advent of wireless communication, radio, television, and satellite technology owes much to Faraday's original insights into electromagnetic waves. Today's digital world, with its vast interconnected networks and devices, could not exist without the foundation laid by Faraday's discoveries. In conclusion, Michael Faraday's legacy is one of unparalleled scientific achievement, intellectual integrity, and dedication to the advancement of human knowledge. His discoveries in electromagnetism, electrochemistry, and optics continue to shape the fields of physics, engineering, and technology, influencing innovations that have transformed society. Faraday's ethical approach to science, his commitment to education, and his belief in the value of knowledge for the public good remain essential guiding principles for scientists today. Faraday's enduring influence is a testament to the power of curiosity, integrity, and the pursuit of knowledge for the benefit of all. His legacy will continue to inspire and inform the scientific community for generations to come.